Unlocking the potential of water electrolysis for space exploration might seem daunting, but recent advances reveal how magnetic forces could revolutionize the process, especially in the microgravity environment of space. But here's where it gets controversial. Disrupting traditional flow control mechanisms with magnetic fields could drastically cut complexity, weight, and energy costs. And this is the part most people miss. Magnetic manipulation doesn't just make electrolysis possible in space. It could render systems more reliable and easier to maintain than ever before. Since the 1960s, providing a steady, low-energy source of breathable oxygen during long-term space missions has been a persistent challenge. The absence of gravity on orbit impedes natural phase separation. Think of the way bubbles stick to surfaces, making water splitting in orbit more complex and energy-intensive. The current systems, such as the proton exchange membrane (PEM), electrolyzers on the International Space Station (ISS), require heavy auxiliary equipment like centrifuges and pumps to separate gases, consuming around a third of the space station's core life support energy budget. These intricate systems are prone to failure, demanding spare parts that pile up in cargo, increasing mission weight and reducing reliability, factors that threaten future missions to destinations like Mars. Enter magnetohydrodynamics, MHD, a field exploring how magnetic and electric forces can induce fluid movement. Has been studied on Earth for decades, mainly to optimize electrochemical processes. These forces can generate macro and microscopic convection currents in liquids, enhancing gas bubble detachment from electrodes, a key bottleneck in microgravity. The core idea: by applying magnetic fields, we can create controlled convection within the electrolyte, encouraging bubbles to break free more easily and flow toward collection points without the need for moving parts. Specifically, two physical effects come into play. 1. The Lorentz force, resulting from the cross-product of electric current and magnetic field, which drives liquid convection on a macro scale. This macro convection can clear bubbles from electrode surfaces, increasing current density and overall efficiency. 2. The magnetic polarization, MP force, stemming from the differences in magnetic susceptibility between water, gases, and liquids, which exerts localized magnetic buoyancy. This effect can direct gas bubbles away from electrodes and toward collection zones, especially useful in microgravity's lack of buoyant forces. And this is the exciting part. While these magnetic forces are well understood on Earth, their application in microgravity is still largely uncharted territory. Initial experiments conducted in a drop tower simulating near-zero gravity conditions showcase promising results. By strategically positioning strong permanent magnets, similar to those found in common industrial applications, they observed up to a 240% increase in current density during hydrogen evolution with platinum mesh electrodes. Gas bubbles were more efficiently detached and moved away from electrodes, reducing foam formation and improving electrolysis stability. In those experiments, the impact of magnetic forces on bubble dynamics was vividly clear. In microgravity, without the natural separation driven by gravity, bubbles tend to form a froth layer that blocks electrode surfaces. But with magnetic fields, bubbles rapidly detach and spiral toward the magnet, mimicking the natural buoyant movement on Earth. Video footage captured the bubble's journey, revealing how magnetic polarization and MHD-driven vortices can create natural vortex-based phase separation, essentially a magnetic centrifuge that outperforms mechanical stirrers, which add complexity and potential failure points. One of the key innovations demonstrated is a proof-of-concept PEM electrolyzer that uses diamagnetic forces, those arising from differences in magnetic susceptibility, to actively control gas bubble detachment and collection. The magnetically enhanced design achieves performance comparable to terrestrial systems, yet without moving parts or complex mechanical components. It simplifies the architecture, reduces mass, and tackles reliability issues head-on. In parallel, a new type of MHD-driven device was tested, a circular, vortex-inducing system that spins the fluid via Lorentz forces, forcing bubbles to the center for easy extraction. Although microgravity experiments are short-lived, their results show that the vortex flow mechanism can reliably separate and collect gases, an important step towards scalable space systems. The implications are profound. Magnetically induced convection and phase separation can pave the way for lightweight, robust, and energy-efficient oxygen generators for long-duration missions. These systems could replace bulky, failure-prone mechanical devices, reduce mission mass and power demands, and make sustainable space mining of water and production of life support gases more feasible than ever. And here's the big question to leave you pondering. Can magnetic technology truly become the new cornerstone of space-based electrolysis? Or are there still unseen challenges, like long-term magnetic stability or integration complexities, that we need to solve before space agencies adopt this approach? Share your thoughts in the comments.